So let's continue with the substitution method. Let's try it on this integral. Let's find the antiderivative. Do you see what we need to choose for our u substitution? X cubed minus 1, right? It's really inside the 1 divided by u to the 5th function. So we'll see that here in a minute. So u is equal to x cubed minus 1. So what's the derivative of x cubed minus 1? That's simply 3x squared. So du is 3x squared dx. Now I look back over here, I've got a 5x squared dx. Here I've got 3x squared dx. To fix that the way I'm going to do that to get a 5, what do I need to multiply 3 by to get 5? Well, the answer is 5/3. 5/3 of du. 5/3 times 3 is just 5. And there is my sort of balanced relationship now. So up top, 5x squared dx, that's just going to be 5/3 du. And I'll have 1 divided by u to the 5th. And so I'm going to pull that 5/3 out. Constant multiple of 5/3, right? Because the 5x squared dx is 5/3 du, so there's my du. I have to keep that in there, and down below I just have x cubed minus 1, which is u to the 5th power. There's the substitution. Now I can evaluate this integral. Of course, I do need to rewrite this. 5/3 times the integral of u to the negative 5, and then I use the power rule, right? 5/3 u to the negative 5, so I'm going to add 1. All right, divide by 1, and then plus rc. Clean this up then. I've got negative 1/4 times 5/3. The u to the negative 4th comes down. I get 5 divided by 12 u to the 4th. Negative, that is 5 divided by 12 u to the 4th. So again, 5/3 times negative 1/4 gives me the negative 5/12. U to the negative 4 comes down as 1 over u to the 4th. Okay, and then the final thing, of course, remember, is to indeed go back to the original variable, but that's simple. We simply replace u with x cubed minus 1. And just sit back and look at this. You know, this is a pretty powerful thing we've done. If we started with this when we first started talking about antiderivatives, you know, if I asked what's the antiderivative of this function, that would have been very challenging to do. But this substitution method makes this much very easy process in a sense. So very helpful. Okay. The next one, this integral looks pretty easy, and you might be wondering why it's even here, because I don't really see a composition of two functions. I just see tangent of theta. The variable here is theta. We're saying, what's the antiderivative of tangent theta? Well, you might be saying, well, wait a minute, isn't that secant squared theta? Be careful. Derivative of tangent theta is secant squared theta, but we're not looking for the derivative. We're looking for the antiderivative. Which function has its derivative tangent theta? And we don't know that. You know, interesting enough, we don't know the antiderivative of tangent theta, cotangent theta, secant theta, or cosecant theta. We have yet to learn those. Well, we're actually going to learn tangent theta right now, and then I'm going to encourage you to do cotangent theta in a similar manner. So how would we do this, and why is it here in substitution? Well, I'm going to use an important trig identity that you should recognize, the ratio identity. Tangent theta is sine of theta divided by cosine of theta. You remember that one? Yeah, tangent theta is sine theta divided by cosine theta. You say, well, how is that going to be helpful? Well, now what I'm going to do is I'm going to do a substitution. I'm going to let u actually be the bottom function cosine theta. You might say, why am I going to do that? Well, look what happens here. Du, what's the derivative of cosine? It's negative sine theta d theta. You got to be careful about that. We bounce between the derivative of cosine theta and the antiderivative of cosine theta. You got to remember the derivative of cosine theta is negative sine theta. The antiderivative of cosine theta is positive sine theta. So it's a little tricky thing to remember. Well, I've got a sine theta d theta, so it's negative sine theta d theta. So if I multiply both sides by negative 1, I get negative du is sine theta d theta. And you see what I have now? This changes this integral into what form? The sine theta d theta is minus du, so I've got the -1 comes out here, du over cosine theta, but that's just u. This is 1 over u du. What integral is that? That's natural log absolute value of u. All right? Of course, I've got this -1 in front of it in this case. And there it is. There is the antiderivative of this. I do have to go back to the original variable, but that's easy because u is cosine theta. So the antiderivative of tangent theta is -1 times the natural log of the absolute value of cosine theta. Okay. Now, there's another form that this can be written in. There are properties of logarithms that come into play a lot of times, and if you're finding an integral, you might see the form of your antiderivative looking different. And let me remind you real quickly of those, of one of those properties, and that is if I have the natural log, say of let's do a to the n, right? The natural log of a to the n, then I can, right, by property of logarithms, bring this exponent down essentially to n times the natural log of a. If you remember, that relationship comes from the fact that logarithms are exponents, right? And when we're finding the logarithm of a base rate of an exponential expression raised to another power, what do? We multiply the powers. So we're going to take a the power on the logarithm a to the n, right? So we want to find the exponent here, and the process of raising one exponent to another, we're going to multiply. All right, so that's where this comes from. Some other ones that you might be familiar with as well is a product, right? When we're multiplying like bases to different powers, what do we do with their exponents? We add them. And so this is the property. And then, of course, if we divide, we subtract the exponents. Again, the logarithms are indeed the exponents. So, but this is the one I'm going to make use of real quick here in this sense, and that is I'm going to write this as the natural log of the absolute value of cosine theta to the -1 power, because I can bring, in sort of going from this expression up here, I can bring the power up. That's what I've done. This is a -1. I've brought that up here. And what is the reciprocal of the cosine? That is the secant function. Okay, so this is one way to write the antiderivative of tangent theta, and here is another that is equivalent just by properties of logarithms. So the natural log of the absolute value of secant theta is the same as -1 times the natural log of the cosine function, because remember, the cosine theta to the -1 is 1 over cosine. 1 divided by cosine is secant theta. Okay, so what I'd like for you to do, is to find the antiderivative. I want you to find the antiderivative of cotangent, if I can get it written out here with this pen, cotangent theta d theta. Do that one on your own and see if you get, it's going to be very similar. Of course, here tangent was what, sine over cosine, so what are you going to do? Cotangent theta is what? Cosine over sine. Instead of u equals cosine theta, you'll do u as sine theta. Work it out and you'll get something similar to what we have here. That'll be the antiderivative of the cotangent function. Okay, so kind of an interesting one. Let's look at a couple more here. Here's some interesting ones. Secant squared of the square root of x divided by square root of x. What is that antiderivative? Well, that's very tough, but the substitution method is going to make it easy. What are we going to choose our u to be here? Which is the inner function here. If you said the square root of x, then I would agree with you because it's inside the secant function. Now some of you might say, well, secant squared, secant of square root of x squared, so secant of square root of x is inside the squaring function. And you might say, well, let's let u be secant of square root of x. I mean, we did something similar to that in the last video. But the problem is that, right, you try and find the derivative of that inner function. Derivative of secant u, if you remember, is secant u times tangent u, and I don't have any extra secant u's or tangent u's floating around, so that's not going to get me anywhere. This one actually will, because look what happens when I find the derivative of x to the 1/2. Remember, that's 1/2 x to the negative 1/2. And so if I clean this up, bringing this as 1 over x to the positive 1/2, or 1 over the square root of x, I get du is dx over 2 times the square root of x. Now I've got dx over the square root of x, so to get rid of this 2, I just multiply both sides by 2. So 2 du is dx over the square root of x. And so the dx over square root of x is just going to be 2 du secant squared u, and so my integral becomes the dx over square root of x, 2 du, bring that 2 out, secant squared of what? U, and du. So 2 du again is the dx over square root of x, and the secant squared u. Everything's transferred to this new variable. What's the antiderivative of secant squared? We do know what that is. That is tangent. Yeah, because we said that the derivative of tangent is secant squared, so the integral of secant squared is tangent. And then I can go back to the original variable. Since u is the square root of x, this is 2 times tangent of the square root of x plus c. So very simple when we use substitution and how to attack these. Okay, now look at one more here, real important one. When we are doing substitution, sometimes it requires a little extra work, and this is an example. Okay, if I ask you to do this with substitution, I hope that you would say, let's let u be 2x minus 1, because that's inside the square root function, right? And so we take the derivative of 2x minus 1, that's just 2. So du is just 2 dx. Now here's the problem. I've got 2 dx, I've got square root of u here, right? Square root of u, but then I've got a 2x dx, and this is just a 2 dx. Now you say, okay, what am I missing? The x. You say I multiply both sides by x. That's a problem, because over here you'll have x du. You don't want to have the u's and the x's mixed together. You don't want the u's and the x's mixed together. Okay, so how can we do this? You have to get everything turns in terms of u. Well, look back here at this original substitution. I got u in terms of x. Can I get x in terms of u? Yeah, I can solve for x, and that'll take care of that extra x that's there. So in other words, I can do what? Add 1 to both sides, and let's swap sides too. So 2x would be equal to u plus 1, and then I can divide by 2 to solve for x, or I'm going to multiply by 1/2 is what I'm going to do. So 1/2 times u plus 1. Okay. And now I can take that value of x, all right, and that value of x can go in for x here. Okay, so x is 1/2 u plus 1, so I'll let it be that, and then the under here I've got the u, and then what do I have left? The 2 dx. Now 2 dx is covered there, and so my antiderivative becomes the integral of x, which is 1/2 u plus 1. So that right there is the x part of things, right? That was the x from there. And then I've got the square root of u, or u to the 1/2, right? That's the square root of 2x minus 1, right? And then I've got the 2 dx, and the 2 dx is the du. So see how everything is covered there? Everything is changed over. All right, let's clean this up a little bit. I'm going to pull the 1/2 out here. I'm also going to distribute here. I need to distribute this u to the 1/2 through. And so I get u to the first times u to the 1/2, add the exponents, u to the 3/2, and plus 1 times u to the 1/2, and then my du. And so it's a simple power rule, right? So this becomes 1/2. Antiderivative here is add 1 to 3/2, which is 5/2, 2/5 u to the 5/2, plus add 1 here, 3/2, 2/3 u to the 3/2, plus c, now that we find the antiderivative. And we can clean this up. I can distribute the 1/2 through, and then I will also go back to the original variable, right, which is u being 2x minus 1. So 1/2 times 2/5 is 1/5. U was what? 2x minus 1 to the 5/2 power, plus 1/2 times 2/3 is 1/3. U again, 2x minus 1 to the 3/2 power, plus c. Okay. So that's one way. Now, there are other ways you can do substitution here that will work as well. The key is, again, you've got to get everything sort of covered here, right? So we started with the integral of 2x square root of 2x minus 1 dx, right? But everything is transformed to its corresponding expression in terms of that substitution of u equal 2x minus 1. I did have to solve for x here to do that, but that's the way you would proceed with that. Okay. Okay. We'll stop, I think, with that. And the last video, what we'll look at then is how to apply this substitution method when we are dealing with definite integrals. And that is what we usually refer to as change of variables.